हेलो गुड मॉर्निंग एवरीवन ठीक है हेलो हेलो ऑफ कर दे
Hello, good
Hello, good
morning.
morning.
Check.
Good morning, everyone. Distinguished guests, esteemed speakers, and participants from around the world. I am Stuti Bej, and with me is my friend and co anchor Nitish Nanda, pursuing undergraduation at Stuart Science College. It is our honor and privilege to welcome you all to the second day of Caosa 2025. Yesterday, we witnessed enlightening discussions and innovative ideas in the field of optical spectroscopy. Today we continue this journey with three exciting sessions that promise to bring us deeper insights and practical applications of spectroscopy in various domains. To begin with, let me first acknowledge and welcome the chairperson of the third session, Professor Dr. Ratan Kumar De. Please join me in welcoming Dr. De with a hearty round of applause. Sir, we are privileged to have you with us. Today, we converse to explore, discuss, and shape the future of spectroscopy, a field that continues to illuminate new paths in science and innovation. So, without further delay, let's move forward and know about our today's first speaker of the third session, Professor Dr. Lekha Paramanik.
Dr. Paramanik is the senior postdoctoral fellow at John Book National University, South Korea. She is a distinguished researcher in advanced nanomaterials. She is internationally recognized with over 1100 citations and an H-index of 17. She has published in leading SCI journals such as Chemical Engineering Journals, Applied Surface Science, Nanoscale, Inorganic Chemistry, and Composites Part B Engineering. Her signature innovation, dual interface nanoarchitectures, has transferred the field of photocatalysis by enhancing charge transfer mechanism and improving performance under visual light. Through this visionary approach, she continues to shape the future of sustainable energy and environmental technology. It is my honor to welcome ma'am, who has graciously joined us today to share the valuable insights. We are delighted to have you. So please welcome Dr. Lekha Paramanik.
Good morning. Good morning to everyone. First of all, I would like to thanks for such a nice introduction. In the ongoing seminar, we are learning and sharing knowledge about optical spectroscopy techniques in detail. Today, in my presentation, I will be explaining about how I am using various optical spectroscopy techniques in my daily research work. The core topic of my presentation is magazine modified heterostructure for photocatalytic application. Here is the...
Hello.
Hello.
Hello, am I audible?
Yes. Yes, sir.
Ma'am, we are not able to see your slide, or we are not able to see you also.
Sorry, sir. Let me
On the
check once.
screen, kindly. Okay. Okay. Perhaps you are not connected.
But I can...
It's not visible. The slides are not visible, ma'am.
Incidentally, Lekha is my niece. Lekha,
हाँ,
तो देखा जाऊनी तो तू देखा जाऊनु कि तो स्लाइड देखा जाऊनी तू कनेक्ट कर
ଗୋଟେ ମିନିଟ୍ କାକେ
कके कहूची
ଆଜ୍ଞା କାକେ
हाँ.
This one.
That is the sir online trouble actually. Yes. Now it is visible, ma'am. The slides are visible now, ma'am. Okay.
Just a moment, sir.
Now it is okay. Oh yes, ma'am, you are not visible actually on the screen. Now it is okay, ma'am. Kindly continue.
Thank you. Am I visible and screen is visible?
Yes, you are visible, very much visible.
Thank you. Sorry for all this. In the ongoing seminar, we are learning and sharing the knowledge about optical spectroscopic techniques in details. Today, in my presentation, I will be explaining about how I am using various optical spectroscopy techniques in my daily research work. The core topic of my presentation is magazine modified heterostructure for photocatalytic application. Here is the outline. I'm unable to my work. Here is my outline of my today's talk, which starts with the introduction of various optical spectroscopic, and further I will dive into the effective utilization of some of optical spectroscopy such as FTIR, UV visible, PL spectroscopy for analyzing a photocatalytic material and their correlation with the activity result and structural changes. Before going into the instrumentation and further details, we would like to say few words on how light interacts with matter. Yesterday, we have seen that Professor Ashok sir gave a fantastic outlook of it. However, the continuity, I am discussing this aspect briefly. We all know that light can be absorbed, scattered, transmitted, and emitted. And all the various optical spectroscopy rely on one of these fundamental phenomena. For example, absorption phenomena is mainly involved in UV visible spectroscopy, whereas the Raman works on the basis of scattering of light. In FTR, we study the transmission of IR radiation with matter, and the emission phenomenon is exclusively useful in photoluminescence spectroscopy. Here we can see the image of various advanced optical spectroscopy techniques such as FTIR, UV visible, PL, TRPL. As I mentioned earlier, we use IR region for FTIR spectrum, whereas the UV visible and NR spectral portion of the electromagnetic spectrum is utilized in UV visible and PL spectroscopies. Let's deal into the FTIR instrumentation. This is the pictorial depiction of the FTIR instrument that could be look like. It has an interferometer and an FFT computer to couple the Fourier transform, which ultimately helps to deliver the final FTIR data. Next to that, we can look into the various regions such as fingerprint region and functional group regions. We know that fingerprint region is critical for identifying the unique molecular structure, as it contains a unique pattern for each and every molecule. Following the fingerprint region, there are the functional group regions covering the single bond, double bond, and triple bond stretchings. It is important in the FTIR spectroscopy to know that a material to be IR active, it must have a change in dipole moment when it has interaction by the light. This properties allows the molecule to interact with the IR light, resulting in the transmission that we can measure. Among all the various regions of electromagnetic spectrum, IR region is the optimal for analyzing various bond interaction such as bonding, such as bending and stretching vibrations. Next, next I'm going to cover the UV visible spectroscopy. From the instrumentation, we can understand that it consists of a light source and a monochromator to choose a desired wavelength, and a detector that collects the final observance and reflectance. UV visible spectra measures the interaction of light with matter, causing electron transition from ground state to excited state as shown in this figure. The transition between the energy levels such as bonding to antibonding or non-bonding to antibonding can be explained on the basis of molecular orbital theory, which is as a result it can show the shift in the spectral of the UV visible. Shift in the wavelength represent hypsochromic and barthochromic shift, whereas change in the intensity of the observance is referred to the hyperchromic and hypochromic shift as shown in here. Next, get into the some points related to photoluminescence. Photoluminescence spectroscopy is a technique used to study the emission of light from the material after it has absorbed photons. Like we did in the previous slide, that it also, let's start with the instrumentation. PL has a light source, and when sample is irradiated with an excited monochromator wavelength, it emits emission peak exhibiting radiative and non-radiative luminescence behavior. This is the Jablonski diagram, which serves as a tool for understanding various emission mechanisms based on the time scale. As presented in the Jablonski diagram, we all know that fluorescence occurs immediately because it involves singlet transition, whereas the phosphorescence phenomena takes time since it occurs from triplet excited state to ground state. In non-radiative process, absorbed energy is dissipated as heat, while in radiative process, energy is released as photon producing light. Using PL spectroscopy, we can study and understand the size of a material also at nanoscale level. In particular, in nanomaterials, quantum size effects correlates the emission wavelength with the size of the particle. Additionally, the PL intensity is exceptional in understanding the charge recombination rate. That's why it is very much essential in understanding, therefore it is very much useful to understand the essential charge transfer dynamics for deriving a possible reaction mechanism in our photocatalytic applications. Next, since I'm going through the plotting, analyzing that data for each and every research work of mine, I hope giving a brief idea on how to collect raw data, plot it, and analyze in FTR, UV, and PL analysis would be helpful for the upcoming researchers. So, in this slide, I would present about FTR data at first. In FTR, background scan should be taken frequently because the instrument atmosphere and electronics can drift over time. In ATR, the sample must be in intimate physical contact with the crystal surface. Insufficient pressure leads to weak, distorted, and unreliable spectra. This shows how a raw data is generally obtained from the instrument of FTR. It comes in two columns. as a wave number for such transmittance. Then by using this, taking this raw data, it is plotted by using some graphing software such as Origin. Thereafter, once we plot the graph, we use the screen reading and we can interpret the data carefully. Finally, after labeling, the graph would look something like this. Next, this is the UV visible data that in this slide would be going to talking about. In UV visible spectroscopy, blank analysis is crucial for each sample to subtract the observance of reference solvent. Each analysis needs to be done along with baseline correction for reliable and comparative results across the set of samples. In UV visible in UV visible spectroscopy also, we obtain the results in two columns, which is wavelength versus observance. Then this data are plotted using some graphing similar to previous FTR result using Origin, and after complete analysis, we determine get information related to absorption capability, such as its absorption aids. Further, I would like to share about PL data interpretation. Contrary to the FTR and UV, in PL, at first we have to give an excitation wavelength as input. Thereafter, we can collect the PL signal of corresponding sample. Then this PL data is plotted as shown here, and we can adjust the wavelength region for better appearance in our manuscript. The baseline correction and normalization with respect to the relative intensities are essential for our studies to evaluate the emission peaks shift for a set of samples. Normalization is also mandatory to correlate the peak shift with particle size. From this slide onwards, I would like to present my recent research work, which I have carried on magazine modified cobalt iron LDH and cobalt iron chromate heterostructure. Before sharing the optical results and discussion, I would like to present the synthesis protocol and some detailed objectives of the work. For better interface formation with sufficient active sites, I have involved in situ hydrothermal approach for synthesis. For the from this synthetic schematic representation, we can understand the order of adding precursor material to get the final ternary product. This product, cobalt iron LDH, cobalt iron chromate modified with magazine, behaved as a multifunctional photocatalyst. Hence, I have performed photocatalytic hydrogen evolution, TCS degradation, PC water splitting analysis to evidently present improvement in charge carrier lifetime and propose a charge transfer mechanism, which I will presenting in the later slides. Now let's get into the complete FTR analysis of pristine cobalt iron LDH, which have abbreviated as CFL, and the binary, that is cobalt iron LDH, cobalt iron chromate heterostructure, which is as CC, and magazine modified the binary system with several weight versions, and it is represented as CMC in this graph and also in the coming slides. From the graph FTR spectra, we are comparatively analyzing the various functional group, and finally I found that the wedge bending is observed in the region between 3600 to 2900, which is the hydroxyl groups present in my photocatalyst material. Then as I have discussed previously, the fingerprint region is the region where the unique pattern for every molecule gets appeared, and for titanium carbide magazine, as here we can see that 602 is the peak, which correlates to the TIC bond, and further the metal oxygen bond related to cobalt iron LDH as well as cobalt iron chromate metal. They appear in 400 to 1100, such as 831, 692, etc. Besides, the carbonate ion that are present in the intergallery of LDH material, those appear as those CO stretching appear in 1505 and 1358 on all my modified catalysts. The complete conclusion that I draw from the FTR analysis is that shows that my material was synthesized in pure form. We are having structural analysis. Since all the peaks related to my related to the parent material are present in my final ternary. Therefore, it gave me confirmation that my ternary material has been prepared, and also the ternary material has shown hydrophilic nature, which is very much beneficial towards the photocatalytic reaction. Now let's move towards the detail about the results of absorbance spectra of CFL, CC, and CMC sample. And the figure B and C represents the optical band gap that I derived from using the Kubelka-Monk function. The absorbance spectra shows that the CMC material has the absorption rates above 650 in contrast to CFL, which was near to 600, indicating that visible absorption capabilities has improved in the ternary sample. This is the PL results of my CFL, CC, and CMC 7.20 sample. From this A figure, we can observe the PL spectra, and figure B depicts the normalized relative intensity of the three material. And from the PL graph, we can graph the intensity directly correlates with the charge recombination rate. Higher the PL intensity, higher is the charge recombination, and ultimately it will contribute to a low photocatalytic performance. Next, this is the result obtained from the PC analysis for piston CFL, then modified binary CC and CMC 7.5. The figure A and B is the Nyquist plot that is obtained from the electrochemical impedance spectroscopy. The electrochemical impedance spectroscopy delivers the information regarding the charge transfer resistance that is operating between the electrode and electrolyte interface, and it is directly correlated with the PL intensities. Figure C is the photocurrent response and it is also completely inconsistent with the PL intensities. The figure D is the linear sweep voltammetric curves of all the three samples, and it can be seen that the optimized CMC sample shows the highest photocurrent density as it highest density as has is the least PL intensity. This here in this slide, now I am discussing about delivering the results that are obtained from.
Professor Lekha,
Yes,
another 5 minutes, please, you conclude because next speaker is online, I think.
yes, sir.
Okay, thank you.
This slide delivers the results of TCS degradation. Figure A represents the photocatalytic degradation of TCS molecule. B is its corresponding kinetics, and it fits to the pseudo first order rate constant. And the highest rate constant was observed for the CMC 7.5, and D is the absorption spectra for TCS degradation by CMC 7.5. This is the result that I result obtained from photocatalytic hydrogen production of all the samples, and the highest rate was obtained for CMC 7.5. The table in this table correlates the activity with the PL intensity. The metal with high PL intensity shows the low result. Finally, after concluding all the results, I was able to give a possible reaction mechanism, which is helpful in understanding the trans-surfactant dynamics in my material. The cobalt iron LDS has a optical spectroscopy, optical band gap of 2.75, and in combination with the valency band analysis, valence band and conduction band, I was able to determine with minus 1.83 volt. Then after the heterostructure formation, it has the conduction band of minus 1.74, and by using the UPS analysis, I found that the titanium carbide magazine has a Fermi level of minus 1.0. As it's a metallic character, it has a very higher work function with low Fermi energy level. As a result, the electrons would migrate from the conduction band to the titanium carbide magazine surface, and the electron will be abundantly available for the photocatalytic application. This is a complete comparative tabulated summary of my results. From FTR spectroscopy, I able to determine the structural integrity was confirmed, and from the UV visible spectroscopy, I concluded that with the modification, the absorbance has been increased, and it is as a result, the activity rate has been highly improved. The photoluminescence spectroscopy produce the emission peaks across this range 450 to 750, and with the intensity comparison, I found that the final my CMC 7.5 has a very high charge transfer efficiency. This is the last on my. I would like to conclude with that the optical spectroscopy proved essential for understanding the photocatalytic mechanism in the complex heterostructure, whereas the FTR, UV visible, and PL trilogy provided comprehensive metal characteristic for synthesis to application. The spectroscopy evidence directly correlated with my photocatalytic performance. Methodology established for rational design of next generation photoly helpful for using optical characterization. Thank you very much for your kind attention, as well as I would like to thankful to the giving me this opportunity to deliver a talk in front of my respected teachers. Thank you very much for this opportunity.
Are you able to hear me, Lekha?
Yes, sir.
So very nice presentation. So we can take up only one two question. So let me ask you one question. Uh,
Yes, sir.
I am chairing your session. My name is RK De. You can recognize me. I am the student of Professor Sudhanshu sir. Okay.
Yes, sir.
So my question is that you are working with the LDH, layered double hydroxide, a phyllosilicate kind of material. I am sure.
Yes, it's hydrolyzed.
Phyllosilicate material. So suppose I will take microporous or mesoporous material. Do you think that the charge transfer will be better than the phyllosilicate kind of material? Because in phyllosilicate kind of material, perhaps for charge transfer you are depending upon the layered structure, if I'm sure,
Huh.
right?
LDH has
So
a 2D metal layer structure.
Yes. So if I suppose take microporous or mesoporous kind of material instead of phyllosilicate kind of material, do you think this photocatalytic activity will be better with the using the M gene?
Yes, sir. With the when LDH has the lifespan of the charge photo-generated for lifetime of the generated electron hole is relatively low because they gets combined very easily.
Okay.
When I have shown that modified with the magazine, I found that uh, it has improved the capacity.
Okay. So you are doing also that the layer structure, the adjustment also you are doing. Means you are preparing various kind of layer double hydroxide by this that is called your the D spacing you are also changing. Yes or no?
Yes, yes. With the modification, the D spacing also changes.
Okay, okay. Thank you. So,
Thank you.
sir will ask you one question, perhaps.
Thank you, sir.
Hi, this is Sudhanshu Tripathi, Dr. Miss Lekha.
Again, okay. Yes, sir.
No, in English. I don't,
Yes,
I don't understand Odia, right?
yes, sir. It's
Okay, in your slide, I think there is by chance a mistake. If not, you clarify. The OH bending you have written 3400 to 3600. Would it be OH bending or OH stretching?
stretching.
So make a
Oh, that
correction
is
in that slide. Okay,
yes,
if I'm correct. Okay.
yes. It is road stretching. As
Okay,
one
no,
six
no,
minute.
it's okay. It's a by mistake. That
Yes,
should not be there in your slide.
yes.
Number
Sorry.
two, why do you say it is PL? Do you observe any phosphorescence? Why not fluorescence? Are you
It's
having an allergy for the
fluorescence.
term fluorescence?
Yes,
So
it is the uh, it is a fluorescence.
I understand that. So why not you pinpoint that it is fluorescence? PL also includes phosphorescence. Do you understand?
Yes, our investigation is mainly in the fluorescence region for photocatalytic.
Yeah. And thirdly, the different colors that you showed for different sized nanoparticles, did you prepare them or you have just exhibited them? Different colors
Size.
with the size of nanoparticles, the color emission
Ah,
differs.
in QD.
Yeah.
Sorry.
Have you
No,
prepared them
no.
different
This
size?
is
Only
no.
theoretical. You
This
wanted
is
to.
this is from other.
Okay, okay. Thank
Yes.
you. Excellent, excellent presentation. I'm proud of you. Bye bye.
Thank
Thank
you.
you, Professor Lekha. Okay.
Thank you, sir.
So, next speaker.
Thank you, ma'am, for your insightful presentation. Your expertise and clarity have greatly enhanced our understanding of the topic. Thank you. Today, we gather to share knowledge, insights, and innovation in spectroscopy. With this, now let's know about our next next speaker, Professor Dr. Evelina Georgieva.
Professor Zeroziva is the professor of theoretical chemistry and head of the laboratory of theoretical and computational chemistry at the Institute of General and Inorganic Chemistry, Bulgarian Academy of Sciences. She has an impressive academic record with 73 scientific publications, nearly 1,000 citations, and an H-index of 20. Her research focuses on quantum chemical simulations for materials, energy, and environmental applications. Her expertise spans designing new optical materials, studying proton transfer processes, exploring excited state energy mechanisms, interpreting ultraviolet visible spectroscopy, nuclear magnetic resonance, Raman spectroscopy, and emission spectra. She further enriched her expertise through postdoctoral fellowships at renowned institutions across Europe and Asia, including the Autonomous University of Barcelona, University of Vienna, SES Academy of Sciences, University of Natural Resources and Applied Life Sciences in Austria, and Tianjin University in China. So please put your hands together to welcome Professor Evelina Zeroziva.
So Professor Evelina, welcome to the conference board.
Thank you. Thank you.
so-
Good morning, everybody. Can you hear me? How
Yes,
is the
yes.
picture?
Yes, we are able to hear you.
Everything is okay. Yeah, I see. Thank you. Good morning. First of all, I would like to thank the organizer for the possibility to give my talk and to happy to show you how the experiment can meet the theory. And my talk entitled Dynamic Tautomerism of 2-carbamide-1,3-indandione Determining Factors and Unique Optical Properties. I'm come from Laboratory of Theoretical Computational Chemistry, Bulgarian Academy of Sciences. So first, what we know about this structure? This is molecule, which structure is known, and this structure belongs to monoclinic space group and consists of 4 molecules which are hydrogen bonded due to the donor acceptor and acceptor group. However, this structure could be only determined at low temperature of 120 Kelvin, and this means that the absence of reflections information is about the coexistence of tautomers, why it's not possible to determine in other temperature. This is the question. And second, the yellow needles of Kate center in large temperature interval of 40 degrees. This is not typical for a single tautomer. And when we see the measure absorption spectrum, can you see that the absorptions is in broad range from 200 to 400 nanometers. This is very large region. The molecule characterizes with high photostability and relative safely, and this is a very good candidate for sunscreen agent. Our previous calculations of all possible tautomers predicted that the most stable are 2-NO tautomers, which are 2-hydroxyaminomethylenediamine indan 1,3-dione, called A, this one, and the second 2-carboamide 1-hydroxy-3-oxo-indane. This is B. You can see that they differ with the position of the hydrogen atom, which move between two oxygen atoms. So these our results, experimental, theoretical, are summarized in one published paper in Journal of Computational Chemistry recently. So what we know more about this molecule, the fluorescence spectra showed that we have one high intense emission band, about 520 nanometers. The molecule characterized with high fluorescent quantum yield in solution. However, you can see that the fluorescent band position, shape, and due emission change by different solution. You can see by different excitation wavelengths. So previous calculation showed that this molecule has high affinity for binding to nucleic acid, and the fluorescent emission is sensitive to the concentration of nucleic acid sequences, temperature, and time variation. So this molecule appears suitable as fluorescent molecular probe for the study of various biomolecules. What we want to understand more about this system, we'd like to interpret the observed special optical behavior of KIT, including absorption, different absorption behavior, and fluorescence spectra, which change in various environments and conditions. What is the mechanism of energy absorption and emission? We'd like to construct energy level diagrams of Jablonski for A and B tautomers to estimate excited state lifetime of the relaxation processes, and we'd like to estimate the equilibrium between these two tautomers, which conversions is due to intramolecular proton transfer process in gas phase, solution, and solid state, especially in ground state and including excited state. For that purposes, we need to evaluate thermodynamic stability of these tautomers to estimate the energy barrier of the conversion, tautomer conversion, how tautomer populate depending on the condition and environment, and what is the tautomeric conversion rates. So it is possible to exist these two tautomers in solid state. It's possible to convert each other in solid state. This is the special case. And which are the factors controlling the tautomeric equilibrium and the tautomer conversion process in ground and excited state. And they are very important because they can control absorption and fluorescent properties for different practical applications. So these purposes could be achieved by theoretical investigation applying different theoretical approach at molecular level when we simulate a model single molecule and optimize the geometry of the ground state, first excited state, second excited state, and third excited state. We can model and to optimize the geometry of the transition state, calculate vibrational frequency, vertical excitation energy to simulate absorption spectra, to calculate the emission energy to simulate fluorescence in different solution. We use post-ab initio high-level methods for calculation of this all these property models and properties. We apply different solvent models to simulate the solvent environment. So if you consider, when we consider the solid state models and properties, we apply the periodic level calculations using the crystal structure with unit cell parameters, and we perform the molecular dynamic calculation at different temperature, and also the optical properties in solid state and frequencies calculations using the 4 molecules in the unit cell. Different models are using single molecules, cluster which simulate microsolvation around the molecules. Also, we put this microsolvated with 3 water molecules around the A and B tautomer. We put them in the global solvent environment. We use a periodic structure. Different approaches are also applied to calculate vibrational resolve and absorption and emission fluorescence spectra, where the vibroelectronic correction are applied are taken into account in this simulation. We calculated radiative, non-radiative rate constants and lifetime of deactivation processes in solution. Also, rate constant of tautomeric conversion using corresponding formulas. So first, on the basis of the calculations, we predict the tautomeric population of A and B tautomers in ground state. In gas phase, we can see, this is the interesting reaction coordinate. In gas phase, this is the picture, the relative energy between A and B is small, about up to 1 kilocalorie of mole, and corresponding tautomeric population is 67 for A and 33 for B. The energy barrier was estimated of about 3 kilocal of mole. Solution, global and micro and global models. The picture slightly changed. The relative energy between A and B is larger, and the population all change. In summary, in ground state, A form tautomer is more stable in solution, about 90%. The energy barrier of conversion is very low. You can see this value, and the rate constant are in the order of 370 nanosecond for forward and 40 nanosecond for a reverse reaction. What happens in excited state? The stability of both tautomers change, and the B becomes more stable tautomers, and the population of B tautomers is about 100%. The energy in gas phase, in solvent also, the most stable tautomer is B, and the energy barrier is higher. So in excited state, the trend is reversed, and predominantly the equilibrium is shifted towards B tautomer. So we the first principle, molecular dynamics, was performed to estimate the stability of the two conformers in solid state, and the dynamics is in the frame of the 20 picoseconds. The dynamic simulation are performed at different temperature, 120, 300, and 440 kelvins. So by means of calculation, we estimated integral frequencies of the geometries corresponding to A, integration of the basis of the OH bond, which spread from 1.90 to 1.30 angstrom, and the integral frequency of the geometry of the B. So we can see that this value, which also we can consider the mole fraction of A and B, in solid state, mole fraction of A is larger as compared to B, and we have calculated the equilibrium constant at Gibbs free energy for tautomeric reaction of AB conversion. In this feature, we can see evolution. This is from dynamic calculation results. Evolution of the OH bond length. This is where the hydrogen is mobile. Bond length with time for selected molecule, and corresponding probability distribution at different of these bond lengths at different temperature. So what happened with when compare the temperature increase, we see that the population, considering the mole fraction, the population of A decrease with temperature increase, and the population of the mole fraction of the B tautomers slightly increase. So the equilibrium find change with the temperature increase. So in summary, in solids, the dynamic calculation predicted a dominant presence of tautomer A, but this population change or decrease with temperature increase in this ratio. So this means the results show that the two tautomers, A and B, coexist in solid state, and their its equilibrium varies with temperature. So this result is in relation, explain the experiment which showed that only in 120 Kelvin is possible to determine the solid state structure where the population of A is largest. By means of calculations of vertical excitation energy, we simulated absorption spectra of A and B tautomer. We can underline that only the combined simulation, combined absorption spectra of A and B can reproduce the experimental absorption in this absorption spectra in different solvent. This means that both tautomer exist in solution simultaneously. So based on the calculation, we interpret all observed bands and can distinguish the bands which correspond to A tautomer and corresponding to B tautomer.
So, Professor Evelina,
Yeah.
yeah, may I
Just a moment. Okay.
may
I continue. So, according to the calculations, the first excited state of E appears in this region, but we found that first excited state of B is redshifted, is the first excited state in the long wavelength range. And this is, we can distinguish this to the first excited state of the two tautomers. And we can see that only when applied the vibroelectronic correction, which shift the band shift to red region, about 25 nanometer, we can exactly, or in very good, we can very good reproduce the experimental absorption band. When compare the gas phase and the solvent spectra, we found that increasing solvent polarity results in a redshift of the longest wavelength and favor absorption in the ultraviolet A and B region is very appropriate for sunscreen application. So the band shift to the visible region with the solvent, increasing solvent polarity. Based on the calculation, we found that first excited state in gas phase for A is of n-pi character, and for B this is pi character, but just okay. But in a solution, the character of both first excited state for both tautomer is of pi character. In solid state, the absorption spectrum was also measured, and we calculate absorption spectra in solid state for A and B tautomers. Once again, when we combine both simulation of A and B absorption, better can reproduce the experimental absorption spectrum. We found that we can distinguish the vibrational relaxation and electronic relaxation time are comparable to the solid state proton transfer, which is very fast. This is why in this measurement we can find the spectroscopic properties of both tautomers. once again, as in solution, the band gap of B is lower compared to that of A. This means that excitation or absorption of B is redshifted as compared to that of A. And we found that the solid state packing effect provoked a larger change in the optical and electronic properties as compared to the solvent effect, and the broad intense absorption slope in solid state is redshifted in relation to the band in the solution and falls in the visible region. This means, therefore, the kite appears health friendly for its application of biosensors. And the absorption ability as intensity is larger, greater in solid state, which also enhance its effectiveness as a sunscreen. The fluorescence, this is the experiment.
Yes, Professor, kindly conclude it because your next speaker is online.
Okay. Well, this is the fluorescence spectrum. We also can interpret the fluorescence spectrum, and this intense band is due to B tautomer. This is for A tautomer, and this is for emission from dirt excited state. This is the interpretation of the emission. On this slide, I show you the calculated energy level diagram, and the process means that excitation simultaneous upon UV excitation, both tautomer excited to the most absorptive singlet states, then the energy relax to the usually relax to the first excited state, then the Frank Condon first excited state go to the geometry relaxation, and emission, which we found from first excited state, come from in these energy levels. So, however, the processes in this molecule is more complicated because we find emission for the dirt excited state, and we found predominate emission from B tautomers. This means we have proton transfer in excited state. So, what means some things?
So, is it concluded?
Okay. Okay. I would like. Okay. What happened?
So, Professor, is it concluded?
Okay.
Okay.
Further, okay, I will conclude it. Some things disappears. My conclusion is that our further estimation and calculation will be to estimate the excited state proton transfer in dynamic calculations. So we, based on the calculation and theoretical study, we succeed to interpret and to explain the absorption and emission spectra, and to prove that both tautomer exist in solid state, in solution, and the equilibrium depend on the solvent and the temperature.
Okay, thank you.
Thank you.
Professor Evelina, very nice presentation. So we can take up one to question from the audience. Anybody? Yes. Please ask.
Yes, Professor Evelina, that my question that in Jablonski diagram that we basically concept about fluorescence that different energy state excitation in singlet levels, ground level and excited level that fluorescence concept arise. But whenever we talk about inter-system crossing that when singlet and triplet condition that phosphorus exhibit that any chance here we study more in phosphorus concept that you mention as a fluorescence energy excitation state same state method, that means singlet state ground state and excitation. But whenever you talk about inter-system crossing, then singlet and triplet existence, there is a chance of phosphorus exist in Jablonski concept. We know that any effective spectra analysis further we ahead in phosphorus concept.
Okay, thank you. We do not suggest to the singlet triplet intersystem crossing, and we try to measure, but there is no phosphorescence signals. This means that there is no the triplet and the singlet triplet intersystem crossing. Experiment do not suggest for such intersystem crossing, and there is no signal from the phosphorescence measurements.
Okay. Okay, thank you.
Yes, thank you, ma'am.
Thank you.
So, Professor Evelina,
Yeah.
a very nice presentation. I have just one question, small question. Are you able to hear me?
Yeah.
So,
I'm
what
here.
is this molecular dynamic calculation? What is the basis set that you have primarily considered?
For the further calculation.
Yeah.
Yeah, this is we plan to calculate proton transfer process in excited state, but dynamic calculation in time using Newton X program.
Okay.
This is our further in future our plan.
Okay, thank you.
Up to now, we calculated in ground state this
Okay.
proton transfer and framed the 20 picosecond, and we found this the proton transfer process estimated equilibrium, but for AB tau-to-mel conversion, but in ground state using VASP, using the crystal structure
Okay.
consisting of 4 molecules.
Okay.
You applying a VASP program, but this is ground state dynamic calculation of the proton transfer. Further, we go to for the single molecule, we try to estimate the excited state proton transfer because we have
So thank you. So thank
evidence.
you. I got the
Thank
answer.
you.
So thank you. Very nice presentation. Now we'll move to the next speaker.
Thank you so much, ma'am, for sharing your in-depth knowledge. The way you explained such complex concepts in a simple and engaging manner was truly enlightening. Now, moving forward, let's know about our next esteemed speaker, Professor Dr. Stephen Bellarmine Laponas.
Dr. Bellarmine is a CNRS Research Director at IPCM France. His research focuses on organometallic and coordination chemistry with application in asymmetrical catalysis, bioinorganic chemistry, and material science. He has received numerous honors, including CNRS Bronze Medal 2005, the Coordination Chemistry Prize of the Société des Chemins de France 2009, and the Saint-Mier Prize of the Swiss Chemical Society 2013. Dr. Bellarmine has served as the president of the Coordination Chemistry Division of the France Society and is the member of the Scientific Advisory Board of the Enotech. It is my pleasure to welcome you, sir. So please welcome Dr. Stephen Bellarmine Laponas.
Thank you.
Okay, okay, Professor, please continue.
Can you hear me?
Yeah, you are able to hear you.
Okay. Okay, thank you. So it's really a great pleasure to be here. I mean, through internet, but yeah, it's a shame that I could not reach physically the Congress. So sorry about that. What I would like to share with you today is related to chirality and the limit of what we know about chirality. So the title is Nonlinear Behavior and the Limits of Mechanistic Understanding in Asymmetric Catalysis. So basically, when you have a chiral molecule, what we learn at school is that if you have two enantiomers, then the two enantiomers, you cannot differentiate them because they have the same physical property. Basically, for example, if you have if you want to differentiate, if you run the NMR of one enantiomer and the NMR of the other one, they should be the same. But then if you look at their chiral property, things are different. If you have two enantiomers, if you look at the chiral property, then this property is opposite. Means that you can have a positive value and a negative value depending on the enantiomer. That's, for example, the way you measure the optical deviation of a chiral molecule when you use polarized light. One of the enantiomer deviate the angle onto the right, and the other enantiomer would deviate the light onto the left. So as a result of that, if you look at this property, this chiral property, as a function of the ratio between the two enantiomers, then you have linearity. This is obvious. This is the way you calculate alpha D, optical rotation, and optical purity of a molecule. But actually, this is not always true. And in order to illustrate that, what you see here is a very old example of from Oro and Guettet, where they look at the optical purity of this chiral molecule as a function of the ratio between the two enantiomers. So as a function of the enantiomeric excess, you see that it goes out of linearity as shown here. And even more impressive is you take now the enantiopure molecule, so this molecule, and if you look at the specific rotation, so if you use polarized light, depending on the concentration of this molecule in solution, at high concentration or at low concentration, you see that it can deviate the angle of the light on a negative way or a positive way, which is very surprising, actually. So actually, this is what we call nonlinear behavior. You don't have linear relationship between these properties. So here, the measurement of the alpha D and the enantiomeric excess of the molecule. So this kind of nonlinear behavior, you can have it to any kind of chirality and properties that is related to chirality. And in asymmetric catalysis, you also have this kind of behavior. Basically, what is asymmetric catalysis? You have a chiral catalyst that could be enantiopure, and it's going to react with a substrate and reagent, and then you generate a chiral product. And if you have an enantiopure molecule, then you generate the product with a certain amount of enantiomeric excess. If you don't have the ligand enantiopure, then you have a linear correlationship between the inertial selectivity of the product and the inertial selectivity of the ligand you are going to use. But this is not always the case. Actually, there are some cases where you get a much lower enantiomeric excess, as shown here, compared to the one you would expect regarding this linear correlationship. this is what we call a negative nonlinear effect. And obviously, you can also have the other way, which is called the positive nonlinear effect, where actually you get much higher enantiomeric excess compared to the one you should expect based on the this linearity. And this positive nonlinear effect is very interesting because actually it's a way to generate enantiomer purity to have asymmetric amplification, because you start from a low enantiomeric excess and at the end you have a high enantiomeric excess. So this is a kind of asymmetric amplification. And asymmetric amplification is a very important topic, because we are made of chiral molecule and we are made of homochiral molecules. And any mechanism that can explain why we have this asymmetric amplification in life is interesting in that sense. And nonlinear effect is one of the mechanisms that is believed to occur to explain the homochirality in life. So that's the first reason why actually nonlinear effect is important to study. And there is another reason why nonlinear effect is important to study. That is the fact that such a study, so the relationship between nonlinear product EE and ligand EE, so the shape of the curve, basically the shape of the curves can give you some information about the mechanism. So nowadays we use, chemists are using this relationship to understand the mechanism that can occur in chemical reactions, and specifically in asymmetric chemical reaction, catalytic reactions. So talking about the nonlinear effect brings me to the name of Henri Cagon, who is now retired. He's from Paris-Orsay, south of Paris. He did all the pioneering work in the field, and for the purpose of my presentation, what I would like to share with you is what Cagon called the model ML2 model, where actually it can explain some of some nonlinear effect behavior. So basically, in this model, Cagon proposed that if you have a metal that reacts with a ligand to generate a chiral catalyst, and if there are two ligands onto the same metal, so basically that is why you call it ML2, so two ligands of the same metal, then if the ligand is not enantiomer, which means that you can have the R and the S enantiomers, then you have a very interesting situation, because you generate several active species. And you can have homochiral species, so combination of the two same enantiomers onto the same metal. And you can also have heterochiral species, that is a combination of the two enantiomers onto the same metal. And this situation is interesting because this catalyst, if it's active, then should produce the product with no enantiomeric excess. So this means in this situation, the overall product EE would be dependent on the kinetics of all these reactions. And basically, if the homochiral, if the heterochiral species is much more active than the homochiral species, then you can account for negative nonlinear effect. And obviously, the other way you can account for positive nonlinear effect. This is actually what is occurring in the sharpless epoxidation. So sharpless, the famous reaction that gave the Nobel Prize in 2001. When they look at the mechanism, they found a positive nonlinear effect, and this is because of presence of dimers, and the dimers, titanium dimers, can be homochiral or heterochiral. Another example I wanted to share with you is this famous example from Noyori in 1984 and 89, when they look at this asymmetric reaction. So basically you start from benzaldehyde, react with diethyl zinc or dimethyl zinc, and then you get the chiral product. And when they look at the enantioselectivity of the reaction as a function of the enantioselectivity of the ligand they are going to use, they found a very impressive positive nonlinear effect, which was actually the most impressive nonlinear effect at that time. The Yuri, inspired by the work of Cagon, then look at the mechanism. So first I should say that what is the mechanism here? It's basically that you have a zinc chiral species that interact with the benzaldehyde and the dialkyl zinc to generate this intermediate, and then you generate the product. And if this is actually the real mechanism in this reaction, you should have linearity between the enantiomeric excess of the ligand you use and the enantiomeric excess of the product, because the two enantiomers will compete to each other, which gives you a linearity. And here you see that this is not the case. This is not the case because actually the catalyst, which is shown here with the two enantiomers, tends to make dimers. And as soon as you make dimers, you have two possibilities. The two enantiomers together, as shown on the top, or no, the two below, sorry, or the two enantiomers, together, as shown on the top. So let's say that dimerization favor the combination of the two enantiomers, so favors the formation of heterochords. This means that in this particular case, what you have in reality is a trapping of the minor enantiomers as inactive species. This means that in reality in the system, what remains active is a catalyst that is almost enantiomer, which can account for a positive null effect. You still have very high enantiopurity because in reality in your system, you have a catalyst that is close to enantiopurity. And this is a very easy way to understand why you can have positive null effect. On the other hand, if you favor the formation of homochiral species, dimeric species, you have an artificial decrease of the enantiomeric excess, which means that you can account for a negative null effect. So basically, these two mechanisms can explain why you can have positive and negative null effect. And you can also see very basically on this scheme that you have two limits. The upper limit is the one that you can get when you have the enantiomer catalyst, as shown here, and the lowest limit should be the fact that you get the racemic one. And this is obvious that you cannot go upper or below these two lines. But actually, this is not the case. This is not the case, and what I want to share with you examples of things that show that you can go upper this line or even below this line. So actually, it is possible that you can have a catalyst that is more efficient when it is not an enantiomer. This is what Kagan called hyperpositive null effect. And we found that this kind of mechanism can also account for enantodivergent null effect, basically a system that gives the two enantiomers by simply playing with the enantiomeric excess of the ligand and not changing the major enantiomer of the system. So let's start the chemistry now, and let's have a look on this very simple reaction. When we look at the enantiomeric excess of the product using this ligand, if you look at the relationship between these two parameters, we found this very nice non-A effect. Basically, you have a very, very strong positive null effect. But what is really strange there is that when you lower the value of the ligand EE, so the enantiomeric excess of the ligand, you have an slight increase of the enantiomeric excess of the product. This is very surprising. And if you change now the diethyl zinc by dimethyl zinc, this is even more impressive. You start from 16% EE of the product with the enantiomer ligand, but as soon as you lower the enantiomeric excess of the ligand, you have an increase of the enantiomeric excess of the product. This is what Kagan called hyperpositive null effect, a case where actually the ligand, the system, is more efficient when it is not an enantiomer. And this is actually the first example of this behavior. So we are very excited about this result, and what is even more excited is to explain this kind of mechanism. How can we explain this kind of behavior? And this is what I'm going to share with you now. Actually, we found that in this reaction, if you look at the reaction, if you use the enantiomer catalyst, you have a very clean reaction. But if you don't have enantiopurity, then you have a solid. We isolated this solid and we found that actually the solid that is in this reaction is a dimer of the catalyst, and the dimer of the catalyst has the combination of the two enantiomers, so the R and the S enantiomers. So basically what you have here is a trapping of the minor enantiomers as inactive species, and what remains in the solution is the major enantiomer that give you a positive null effect. So this precipitation of the racemic species can account for this positive null effect, but it cannot explain why we have hyperpositive null effect. So we have to look to another parameter. So in this reaction, what is also important to know is that when you lower the enantiomeric excess of the ligand, this means you have more and more precipitation of this racemic species. And this means that you have less and less active species in your system. So the question now is this shape of the curve related to the amount of catalyst that you have in your system? Is there a relationship between the concentration of the catalyst, so basically the catalyst loading, and the result of the catalysis? To verify that, we look at the reaction by playing with the amount of catalyst, so the catalyst loading, using the enantiomer ligand. And we found that when you have only 20% catalyst loading, you generate 16% EE. And as soon as you lower the amount of the catalyst, you see that the curve is increasing. You increase the selectivity. And this is very surprising because in asymmetric catalysis, usually when you lower the amount of the catalyst, you also have a lower amount enantiomer selectivity. And this is very surprising. So the less catalyst you have, the best is the reaction actually. So now let's have a look on this point. When you use 10% catalyst loading of the enantiomer catalyst, this result actually, based on what we have seen before and what I said, means that you should get the same enantiomer selectivity if you use a catalyst that is only 50% EE at 20 mol%. Because under those conditions, half of the catalyst is trapped as inactive species and it remains 10%. So this means that this point, you can superimpose it onto the NLE study that you have seen before. And we did that for all the points. And you see here, what you see here is a perfect matching between the concentration effect and the Downey effect. We did the same with diethyl zinc and we had the same result, perfect matching between the two parameters. So this means that here, what you have is strictly related to the concentration of the catalyst. So how can we explain now this positive effect? Actually, this is very simple. We have all the ingredients to understand what is occurring here. We know that we have chiral catalysts that are monomeric species. We know that they tend to make dimers, and we know that the dimer that is a racemic dimer, so the combination of the two enantiomers precipitate. So as a result, you trap the minor enantiomers as inactive species. So what remains in solution is the monomeric species that also tend to make dimers. And the monomeric species is the catalyst that react with the substrate to give the product. So now let's imagine that you not only have a single species as active species, but also this dimer is also active. And this is an interesting situation because now you have a competition between two species that are in equilibrium and they both give the same product with different enantiomeric excess. So this means that the overall enantiomeric excess of the reaction depends on this equilibrium. And as you have seen before, this equilibrium also can be impacted by the concentration. And this is indeed what we have seen. At high concentration, if you think that you make mostly dimers, this is the reaction that is occurring. At low concentration, this is the reaction that is occurring. And varying the enantiomeric excess of the ligand also has an impact on this equilibrium. So that's why you have this non-linear behavior. So to verify this mechanism, this means that if this is true, this reaction should be affected by the temperature. Usually in asymmetric catalysis, if you want to increase the enantiomeric excess, you need to lower the temperature. But here, if you want to have a better enantiomeric excess, you should higher the temperature. So increase, you should get a higher temperature to get better enantiomeric excess. So we verified that. This is the curve here. And we could see that when you increase the temperature, you increase the enantiomeric excess. And this is very, very unusual. We also did dosing experiment and kinetics, and all in all this stuff is consistent with a competition between monomeric species and dimeric species to get the product. And this, if the monomeric species is more efficient, then you have a hyperpositive line effect. So what next? So if you think about this mechanism, then this is interesting because you have a competition between two different catalysts, but the two catalysts can, for example, give the two enantiomers, the two opposite enantiomers. And if this is the case, this means that you should be able to see enantiomer divergence. So the switch from one enantiomer to the other enantiomer by simply playing this between this equilibrium. And actually, this is a phenomena that is known in literature. There were actually 3 examples in literature that remained unexplained at that time. And this is, for example, the last example that was published in 2008, where they look at this reaction, they found that you have enantiomer divergence, which can generate the S enantiomer or the R enantiomer. So we could study this this reaction and try to find if we have the same mechanism. Or the other way to prove that enantiomer divergence has the same mechanism could be to find a catalyst that to modify our catalyst to go to enantiomer divergence. So to do that, we started with enantiomer per species rather than starting with scalemic species. And we try to see if we have such an equilibrium between dimers and monomers and to see if you can have enantiomer divergence. So I should say that we are very lucky because we did a very simple change in our system. So instead of using a benzyl substituted nitrogen, we have now a methyl. And if you look at this reaction, so playing with the concentration of the catalyst, and if you look at the enantiomer selectivity of the product, we got this very strange behavior where actually at high concentration, you generate the S enantiomer, and at low concentration, you generate the R enantiomer. So what you have here is nothing but a competition between dimers and monomers, and they both give opposite enantiomers. So the result of the catalysis depends on this equilibrium between the two species. So this result was based on the concentration of the catalyst. How about non-air effect? To find the conditions to get enantiomer divergent non-air effect, we did this study first, where they look at this. We look at the enantiomer selectivity of the reaction as a function of the temperature. And let's start with the blue line. When you use the enantiomer catalyst, you see that you start from the S enantiomer, and as soon as you increase the temperature, it goes to the other enantiomer. If you now use the same ligand with only 50% EE, you have more or less the same behavior. And what is really interesting is in the middle, that is at room temperature. When you use the enantiomer selective ligand, you got the S enantiomer, but if you use scalemic ligand with 50%, you got the R enantiomer. This means that if you look at the enantiomer effect under those conditions, you should see NLE. And this is indeed the case. We did it with this enantiomer, and you see that the enantiomeric excess of the product are quite low. So we did the same with the other enantiomer, and we have the opposite result. So here we are. We could find a catalyst that is enantiomer divergent. And this enantiomer divergence is coming from a competition within these different species. So based on this result, now we could come back to the chemistry and we could make a model of that, considering all these active species, considering all this equilibrium, can now link the enantiomer selectivity of the reaction with the enantiomer selectivity of the ligand. and you can make a model and you can modelize a result. And this is what we did. We could modelize, for example, the first result that we have seen in the early stage of my presentation, but you can also play with this model. And if you play with this model, you can also find that actually it's possible to have catalysts that have no enantiomer selectivity when it is enantiomer, but should have very high enantiomer selectivity when it is almost racemic, which is quite surprising, actually. This is amazing, actually. And we are now, this is a theoretical model. We are not trying to find such a behavior, such an unusual behavior, which I should say. We also came out to look at back to reactions that were studied, like, for example, from this publication, we made a model where we consider the possibility to have a precipitation. And if you consider that, this is an example from 2006 where they found this very unusual nonlinear behavior. And we could very easily modelize that, as shown. This is the blue curve here. So we are now able to modelize results, all the results from the literature that were unexplained at that time. We have a lot of models, and for example, if you look at these papers, you can download Excel files where you can modelize very easily nonlinear behaviors in asymmetric catalysis. So, starting from what was known based on the work of Henri Cagon, we now know that these things can be more complicated. We can have hyperpositive non-effect, or you can have enantiomer divergence non-effect. So the question now is, what next? Is this result only limited to a single reaction and a single ligand, or can we verify that to other asymmetric reactions? So to look at that, we first continue to look at the reactions using ligands that are widely used in the literature, and that is, for example, the methyl diphenyl polynol. And we look at this reaction, for example, that was not, the mechanism was not studied. If you look at the nonlinear effect on this reaction, we have a very nice positive nonlinear effect. And if you look at the impact of the catalyst loading, you have no impact of the catalyst loading. So for example, here, what you have using this N-methyl diphenyl polynol, you have the basic mechanism that can explain nonlinear effect. That is the fact that you have mononuclear species that tend to make dimers, and the heterochiral dimers is precipitating, and you have positive nonlinear effect. So now let's make a little change there and removing this methyl. So let's have a look on the reaction when you have only an hydrogen instead of a methyl, which is a very little change. And we know that the catalyst, the mononuclear species, is exactly the same. If you look at this reaction with this very simple change, what you have is again a positive effect. But now if you use this catalyst and you look at the impact of the catalyst loading, you have a very strange behavior. Because depending on the catalyst loading, you can generate one enantiomer or the other enantiomer. And you can see that this is a very strong change between the two, between low and high catalyst loading. What is even more surprising here is that the reaction is changing during the course during the conversion. So what you have here is the enantiomer selectivity as a function of the conversion of the reaction. And if you have a lot of ligands, so like 20%, the enantiomer selectivity remains the same. But if you have a lower amount of catalyst, you see that you start from a high enantiomeric excess, and as soon as you generate the product, you generate a new active species that induce an enantiomer divergence. So what you have here is a competition between first single species that then react with the product to generate a new catalytic species that is inducing enantiomer divergence. And this is, for example, what we call the SOI reaction. The SOI reaction is a kind of auto-induced catalytic reaction. So in conclusion, if you think about asymmetric catalysis, the way we are thinking about catalysis should be seen more like a system level chemistry where you have competition between different active species. This means that when you want to design a Caosa catalyst and design an asymmetric reaction, the way we are thinking to do that is designing a ligand using a metal, and then you draw this very simple catalytic cycle where you have the reagent and give the product. That's the way we are designing catalysts. The goal when you want to get into selectivity is to play to the possibility to generate the two enantiomers, and as soon as you have large delta G between the two transition state that give the two enantiomers, then you can have an selectivity. But this is true if you have a very simple and single active species. But in reality, what you have seen here is that the active species can make dimers. The active species can make also trimers. We have example. We have seen that the active species can react with the product to give a new active species, which means that actually the selectivity of the reaction is the result of competitions between different active species, and all gives a different selectivity, which means that at the end, it makes it even more complicated. So this means that when you want to design a catalyst, you have to be aware about all these possibilities, and you have to be aware that it's not only limited to a single active species as shown here. So in conclusion of my presentation, what I wanted to share with you is that if you have a low enantiomeric excess in the reaction when you use a Caosa ligand, it does not mean that the reaction is not enantioselective. This means that you can have competitions between active species, and the results could be racemic. And this means that the enantioselectivity can be the result of large amount of active species that are competing together in these reactions. And also what we have seen that as a result of that, you can have a catalyst that can be more efficient if it's not an enantiomer, which is very surprising, actually. But this is actually the case. This means that you should see asymmetric catalysis more than system chemistry rather than classical single active species in the system. So to finish, I would like to thank the people who have done this chemistry, and this is the work of Yannick Geiger, who was PhD, Thibaut Thierry, who was a postdoc with me, and Joseph is currently PhD. I would like also to thank some colleagues and some financial support, especially from the companies and universities. And I would like to thank my colleagues and my students, which is actually a very broad and large international group, because I am the only French on this slide. We have Chinese, Algerian, Italian, Spanish, from Lebanese, Vietnam, and Italian people. And so it makes a very international group. I'm really grateful to their contribution. Sorry, and I would like to thank you for your kind attention. So thank you.
So thank you, Professor Stefan. A very, very, very informative and nice presentation. We can take up 1-2 questions. Okay, so since there is no question, so let me give you a big thanks. And now,
thank you.
So thanks for your presence.
Thank you.
So we'll invite the next speaker, please.
Thank you, sir, for your excellent presentation. It has given much to consider. Thank you. Spectroscopy is the bridge between the unseen world of atoms and understanding of them. With this, now let's know about our very next speaker, Professor Dr. Jagannath Panda.
Dr. Panda is a research professor in the Department of Industrial Chemistry at Pukyong National University, Busan, South Korea. He holds a PhD in chemistry from KIT University, Bhubaneswar, with expertise in metal organic frameworks, and covalent organic frameworks for gas adsorption, catalysis, and drug delivery. He has served as guest faculty and postdoctoral fellow at Indian Institute of Science Education and Research, Berhampur, and project associate at Council of Scientific and Industrial Research, Institute of Minerals and Materials Technology, Bhubaneswar. His technical proficiency spans advanced spectroscopic, microscopic, and computational techniques, and he holds an Indian patent on carbon quantum dots. He has published extensively, contributed to book chapters, and earned several prestigious awards for his contributions to science and education. Passionate about mentoring, Dr. Panda is dedicated to advancing sustainable scientific innovations to address global challenges. Having him today is an honor for us. So please welcome Professor Jagannath Panda to enlighten us with his talk.
So, Professor Panda, please. Is online?
It's audible.
Yes, yes, audible.
So thank you for introducing me, and thank you for welcoming me for the conference. So now I will present my talk about. So it's visible now. My screen is.
Yes, yes, it is visible.
Yes. Okay. Thank you.
So please make it full screen.
Yes.
Yes, now it's okay.
Okay. Thank you to the organizer for inviting me to present my work here. So, so when I got the invitation, that time I was doing a job in South Korea. But recently, a few days before, I came and joined as assistant professor in East University, Berhampur. So now I am presenting my work. So my work is mainly, I will discuss about the defect engineering in biometallic metal organic framework, that is MOF. And then synthesis of the MOF, then we use the, as current days now, the device fabrication and the importance for the fabrication of a device and use for the different applications. So then we use the laser induced graphene coating by using this MOF and the graphene coating, then that is applied for the NO2 sensing. So before going to my work, so I will explain why this MOF and how it originated, like from where this MOF came. So before going to this talk, I will discuss about the porous material. So what is a porous material? So that is like link with my material, like my I'm working on a MOF. MOF is like a porous material. So how it will be originated, how it came to the to research, that I will explain. Like porous material is the like we have seen that the nature there are so many porous materials are available. Like in our body, the lungs is also is a porous in nature. It is pumping the air, so it is separating like different which is required, like oxygen is required, that is keeping other gases coming out. Similarly, in case of our bones, like corals and soil is also having a porous nature. That's why it is capturing some like gases that will be used by the plants. Similarly, sandstones and butterfly wings, it is flying because of the air is passing through the wings, that is in porous in nature. Similarly, snow and sea sponge, eggshells and lemon, you have in day-to-day life, we have seen that when removing the water from the lemon, you put in the water, then that again it captures some water in that. That was because that is having some porous nature, so that is capturing that waters. So then from the nature we'll learn that porous metals. Then we'll move to the artificial porous material. What is the artificial porous material? Like we make the porous materials, like paper is porous material because when we're putting on the water, it is absorbing water. And cloths also porous, chalk, bricks, and insulation material like sponge, bread. These are the example of artificial porous material. Then we know this you are using day-to-day life. Then we'll move to the chemistry part. Then in the basis of chemistry or material scientists, they are divided the porous material into depending on the pore size and depending on the framework size. So based on the pore size, the materials are divided into three types, like microporous and mesoporous and macroporous. So what is the microporous material? Microporous material which is less than 2 nanometer size. That example is ZSM5, that is a zeolite. Then micro mesoporous material, that is the pore size between 2 to 50 nanometers. Then the macroporous material, that size is more than 50 nanometers. Like the sponge, whatever available, that is the macroporous materials. Then I will discuss about the based on the framework. Based on the framework, these are divided into three types, like inorganic framework, and organic inorganic hybrid framework, and organic framework. In case of inorganic framework, that is containing some metals, and organic or inorganic hybrid materials, that is containing a metal as well as the organic material, so that it will make a framework type structure, like a particular frame. Like in house, we are making a frame. Similar, like there is a framework between organic and inorganic. Then organic case, it is having some organic linkers, like maybe different covalent bonds take place, then they are forming the covalent organic frameworks, and MOF is the metal organic framework. Basically, in my research, I will discuss about the MOF, as we are synthesizing MOFs, and we are applying for different applications. So then I will introduce what is the MOF. MOF is a inorganic like hybrid material that is containing one organic linker. Okay, so this is the organic linker and this is the metal ionic node. So they are covalent bonding to each other. They are forming some one-dimensional framework, like example silver pyrazine, and two-dimensional framework, that is like 2D structures. I am giving one example, copper bipyridine complex, that is a two-dimensional framework. Then I'll move to the 3D framework. What happens in 3D framework? Mainly MOF are making the 3D framework. 3D means you can see here. So this is making a 3D structures. This green color showing the metal ions, and this is the linkers. They are interconnected with them, then forming a 3D structures. So I am giving one example, that is MOF5. The MOF5 is having the zinc as the metal source, and benzene dicarboxylic acid, that is BDC, is a linker source. So I am giving one example of MOF. MOF is like you can see here, this is the example of MOF5. MOF5, why this MOF5? So whenever the different MOFs are created, they are having no specific name. Like IUPAC have giving some names to the compounds, but here there is no specific name. So depending upon the nature of the compound, depending upon the where it is synthesized or which lab it is originated, according to that, the name is given. So metal organic framework is having the several names are there, like MOF, having MOF ZIF, zeolite immunization framework, or UIO 66, means that MOF is formed in the University of Oslo. Like depending upon the name of the lab, that is given the names. So this is MOF5, where the MOF is having the blue color showing the metal ions, and linker is showing this is the linkers, and what the yellow color ball inside that is the void. Void means it is a porous part, void part of the MOF. So you can see whenever performing some same image, it is giving a particular structures. As I told you, it is giving a framework. So sometimes it is giving cubic structures, sometimes it is giving tetragonal or octahedral structures. The different structures are coming depending upon the which metal you use for the synthesis. Then in the down part, you can see the images, but there you can see mainly these are the different colors because of the doping. Because I will discuss about the defect engineering and doping of the MOF, how we can increase the stability of MOF. That will I discuss in the later on slides. So when you are doping, that color just changes. Then the highly importance of this material is, you can see here why you will study this material. Because just imagine a surface area of a football court. So that is around 10,000 meters square per gram, or more than that, or more than that. So if you take same like 1 gram of MOF powder, that will be equivalent to that surface area of the football court. Not like a physical surface area, it is inside the, like in chemical surface area. Like there are so many surface area, like outside the surface, or you can fix the gas can be observed on the surface. That is equivalent to that one. That's why we are studying the MOF. It is a highly porous material, and it is a future material for different applications. Then we'll move to the synthesis. There are several methods of synthesis of MOFs are there, like solvothermal method, mechanochemical method, sonochemical, microwave, and slow evaporation method. So most of the case, like people are using solvothermal method because it is like the purity of MOF is more. But nowadays mechanochemical method also used to make the large quantity synthesis like 1 kg, 2 kg or 5 kg scale synthesize using the mechanochemical method, like mechanical force used to synthesize the MOFs. Also microwave methods and slow evaporation method also used. So the advantage is solvothermal method is like you can in normal small lab you can synthesize this MOF using a small like oven you can synthesize. So I'll not focus on more the synthesis methods. I will go to the application part. Then application part, there are so many application of MOFs like basically when the MOF started, it is basically focused on the gas storage like hydrogen storage, methane storage, and other type of flue gas storage can be done. And gas separation, like you can see, like make a membrane of membrane, then that can be used the separation of like ethylene or acetylene gas can be separated. Then photoluminescence property, as well as the catalysis properties, chemical sensing, magnetism properties, and oxygen ORR like water splitting class also that can be used as the catalyst, and charge mobility carrier in case of like electronics application, and proton conduction like in case of fuel cell, MOF membrane can be used as the separator. That is, there are very several application of MOF in different fields. So basically, I will discuss about the sensing part. Like we have developed a sensor that will be sense the NO2 gas, like NOx gas you can sense. So the advantage of, as I already told in the before slide, advantage of MOF is it is highly porosity and we can synthesize very wide variant, like we can change the metal or you can change the linker. You can synthesize various type of MOFs. And the limitations is chemical stability and bulk synthesis, like large scale synthesis also issue. But nowadays it is solved. So many companies, they are starting synthesis bulk scale of the MOF so that we can use for the storage of the hydrogens. Then then I'll discuss about the post-synthetic modification. What is the post-synthetic modification? Post-synthetic modification means we can modify the MOF after the synthesis. Like first step synthesis, we can modify, or in situ method. Like we can add when the synthesis time, we can add some metals. We can modify or transmetallization strategy, or post-synthetic modification or incorporation of metals. We can change the framework. Because when the MOF came, we are synthesizing only ligand and metal. But nowadays, new research coming how to introduce more metals on the surface so that more catalytic activity side will come, or more specific binding side will come, so that it will be applied for different applications. Basically, here in my work, I will discuss about the transmetallization defect. Like we'll use transmetallization strategy so that we'll introduce some defect on the MOF surface, then we'll increase the surface like stability of the MOF, then we will apply for the different applications. So what is the defect? Defect, you can see here, I am giving the one structure here, the MOF structure. So what is the defect? Defect case means you can replace one atom or one metal or one ligand in between the framework. You can see the red highlighted area. We can replace one part of the MOF, but it will not defect the complete structure. It will show same properties, but there is only the missing of any node or any linker that can be replaced, but the stability will be same. So that will be improve the structural stability and also make different applications. Then how can you control this defect, make the defect? You can control the method. Control method means you can change the pH, you can change the control diffusion, you can change the modulator. Different solvent act as a modulator that can be used, or you can change the temperature of the synthesis method. Then it will make some defect in the structure, and it will give the control structure. Then again, I told you there are two type of methods, like de novo synthesis method. Like when you synthesize the MOF, that time you can change the temperature, pH, or different control. Then you can synthesize the using the modulator. You can change. Also another method is post synthetic modification. Like after the one step synthesis MOF, we can modify, like change the ligand or change the metal, or changing etching method means you can etch, like wash with some little low concentration acid. You can etch one metal. Etching means you can replace one metal that can be make the defect. Then what is the benefit? it will be enhance the catalytic property, it will enhance the better gas absorption property, and ionic conductivity will be increased, and the selectivity will be increased, and diffusion, modular diffusion can increase, then flexibility increase, and more active side will increase, which will be give more exposed side for the sensing work. Then I will discuss to my research work, which I am doing in in our lab, the Applied Material Research Laboratory in South Korea, Busan National University, and Pukyang National University. And this work also we have collaborated with Georgia Institute of Technology for the theoretical study. So that I will explain one by one. So you can see here in the synthesis method, what happens, we took two metal ions like zinc metal ion solution and iron metal ion solution, and we use as a modulator TEA, which act as a modulator, and we synthesize by hydrogen method with 80 degree and with 24 hour, we synthesize the MOF with the defect. So what is the defect here? It's like we are replacing one zinc ion with the iron. You can see here in the when the MOP5, I already shown in the past slides, MOP5 showing the cubic structures. When we are introducing the iron in the structure, that is changed to hexagonal, which I proved using the FESM. Then the application part, we use these same powders, MOP powders, we mix with the graphene, and we use this polyamide surface and use the laser technique. We mix the laser induced graphene as well as our metal, and we spray on the surface. Then we develop this integrated electrode, which will be directly applied for the sensing of the NO2 gas. So what happens in this case? In this case, there is change in the zinc to iron exchange, and also there is Fe doping takes place. And we have modified, like optimize the morphology, or also optimize the which constant is the best fit for the structural stability, that we have modified. Then we applied for the NO2 gas sensing. Then this is the setup. This is used in the DGIST, another institute. We have collaborated institute. So we measure the NO2 gas sensing properties. Then and this is source meter, and this is a ventilation system. Then we use this our sensor, our flexible sensor here for the sensing purpose. Then, as I told you, we also carried out the compression study to make the structure like either the iron is replaced or not, and the structure is stability or not. We have studied the synchrotron XRD. We have measured the XRD. I highlighted the points. You can find when the MOP5 is here. When there is introducing the metal ions, there is little bit change in the peak position in the XRD spectra. XRD spectra, there are peak change that is only clearly seen in the structure, that there is no structural change, but there is little bit shifting of the peaks. That is due to the introduction of the atomic radii of the that when the metal is iron is introduced there is increasing the bond length, which is also we confirm from the you can see in the B2 figure, there is little bit change in the bond length whenever introducing the metal like iron into the framework. Then I told you the structural changes in the initial case, the MOP5 having the cubical structures. After the introducing the iron, there is a elongation happens in the axis. That is, you can see here, when this is F10 is 10% doping and 20% doping, there is elongation in the structure, that is structural changes takes place. Also, we have performed the FTIR spectra. In MOP5, it is same. There is no specific peak came due to the presence of same structure. There is no change in the structure, only the metal is changed. Then we study the EDAX spectra. There is changing the elemental mapping. For the each samples, we have carried out the elemental mapping. You can see here in MOP5 there is no iron present, but in case of iron presence, in case of the when you dope the MOP, that is showing the some iron present inside the MOPs. Then similarly, we have performed different spectroscopy technique like UV visual spectroscopy. This is diffuse reflection spectra, solid state UV visual spectra. You can find the peak in the UV visual regions for the MOP5. But when we introduce some metal ions, there is peak in the visible region, the 4 to 500 nanometer. You can see here, this is due to the iron 2 plus present inside the framework. And structural stability. So in case of MOP5, this is highly stable. But whenever introducing the iron, there is stability decreases, but not that much decreases. That is also stability till 600 degrees Celsius. Also, we have performed the surface area measurement. In case of MOP 5, we got the around 1200 meters square per gram. And in case of doping samples, it is little bit changes because of the some metal ions also penetrated in the pore of the MOP. That's why there is decreasing in the surface area. Then this is the pore size distributions. So in case of MOP 5, there is big pore, but similar pore also available in case of the defect MOPs. Then we also perform the XPS spectra to identify the presence of the oxidation state of the metals like iron present or not. We got that there is no disturbance in the framework. Only the MOP, that this iron is only introduced in the framework. Then the sensing part, we perform the sensing like NO2 sensing. We have performed in the different temperature like 150 degree, 100 degree, 50 degree, and 25 degree. We got in the room temperature. Mainly, we are measuring the sensing property in the room temperature when we are making a flexible sensors. So we perform. It is going good sensitivity and also selectivity. Also, when we give the mixture of N2 and O2, it is showing the performance in case of only N2. You can see the figure number C, there is increasing the concentration, then the sensitivity also increases. So response time also in figure E, it is showing the good response and recover time, like you can reuse the sensor for the sensing of the NO2 gas. Then also we have as we studied, it is happening or not in the high temperature also we perform, like in high temperature also it is showing the NO2 peak is giving more as compared to the N2. Also, we varied the different temperature as well the different samples case. We got the best performance when the metal ion is increasing. Like when there is more iron atom is introduced, the sensitivity properties increases. Similarly, we perform the this for the different samples and different concentration of the NO2 gas flowing. We perform. Then I will move to the like as we are making a flexible sensor. After the sensing, we have performed the rotation. Like we more the samples. It is flexible or not. It will stable or not. That we perform using this. You can see the E1 figure. We are bending the samples and also perform the test so that it is showing changing. Like is there any changes or not? We have performed. It is showing a good flexibility of the mob. So then I will explain the figure F, that is the like mechanism how it sensing. So in our MOP, it is containing zinc and metal. When the N2 gas is or NO2 gas is coming, it is forming a fast O2 interaction, like that different interaction takes place. The oxygen is coming and it interacting, the O minus O2 minus is coming it, and the NO minus takes place, and then it is interacting with the N2. There are several equations are there. I have not presented here. Then the conclusion part, we have developed a highly sensitivity flexible NO2 sensor that using the MOF, bimetallic MOF, and we have used the position modification as well as the transmetal strategy, which is a precision introduce of iron incursion to the framework. Then the LIG and bimetallic MOF hybrid structure can be used as it is highly porous and it is ensuring the rapid transport of the ions so that it will give the more performance. Then the best performance shown by the best, like more, we have doped different percentage of iron. The F30 shows a good performance as compared to the other metals because of the more iron can improve the more sensitivity in the structures. And also this will provide a scalable and versatile platform for integrating semiconductor MOPs into a flexible electronics so that it can be used in the future broader application like gas detection sensors or long-term stability, and also scalable for fabrication process so that we can make a flexible sensor.
So
Then the acknowledge side, I will acknowledge the Pukyong National University, Busan, South Korea, where I worked this synthesis the materials. Also DGIST, the another institute where we sense the sensing and fabrication takes place, and Georgia Institute of Technology, US, for the computational study. I will thank to the Professor Zhang and Professor Kim from DGIST and Professor Zhou from the Pukyong University. Also our lab members, applied material lab members. They support me for the work, and also I give to thankful to the Stuart Science College, the team CSO 2025, and the faculty members giving me the opportunity to present my work here.
okay,
Thank you.
Dr. Panda, very nice presentation. So we have few questions.
Yes,
So
yes,
I
sir.
have a question. Are you able to hear me? Dr.
Yes, sir.
Panda?
Yes, sir. Yes, sir.
So I have a question just now. Why not NOx? Why exactly NO2? Is there
Oh,
any
yes, sir.
success?
Actually, first we have tried with the NOx in a laboratory scale. We have performed we have developed one our instrument that is developed by ourselves. We have make like a mixer NOx and NOx like this mixer. We are generating using some copper, nitric acid and copper. We generate the NOx gas. Then we tested that. After that, we thought that we'll go for a specific gas NO2,
NOx means I am talking about maybe
NO3 and NO2.
NO3, maybe
Yes, yes, yes,
NO5.
sir. Yes, NO3 and NO2. We tested both for first time. Then we thought that we will separate like particular gas. That's why we choose the NO2. But it is working for NOx, NO3 also. But now we are focusing. We'll fix a metal so that this will be particularly for one gas, so that it will make a like flexible sensor in the real lab.
Okay, so it is not sensing NO3.
No, sir. We are now separating the NO2 only.
Okay, okay, thank you. So any question? Sir will ask perhaps.
Hello, Dr. Panda. This is
Hello,
Sudhanshu
sir.
Tripathi.
Yes,
Can
sir.
you see
Hello,
me?
sir. Yes, sir.
Okay, you are coating on graphene, right? Am I correct?
Yes, sir. Yes.
So, what is the cost effectiveness that you foresee in the real application?
Yes, sir. Actually, the graphene, whatever we are using that is like very less quantity, and that is like negligible quantity. That is not impact to the mainly for the flexible and reusable case and making little bit conductivity. We are using that one. Otherwise, very less quantity we are using. That is not impact to the fabrication process.
Have you tried for the commercial viability?
Yeah, we have filed some patents in US patent.
Thank you so much. Excellent talk.
Yeah, thank you, sir.
So thank you. Any other question? If thank you, Dr. Panda, for
Thank you,
nice
sir.
presentation. So we'll switch over to perhaps next session. No?
Okay, thank you, sir.
Thank you.
We sincerely thank Dr. Jagannath Panda for his enlightening presentation and valuable insights. His work on rapid and sensitive detection offers exciting prospects for environmental and wearable sensing.
Thank you, Professor Ratan Kumar De, sir, for your expertise. We are delighted to have you. Thank you, sir. So, now